All right. Let x equal, it's this side. Because we have to be able to apply our apply our property or definition of a logarithm to that side to get the relationship that we're looking for here. We do it to the right hand side, nothing kind of works out well. Okay, so let x equal log base m of a to c. Okay, then by definition of logarithms, we know that m to the x, that base raised to that x, equals a to the c. You guys agree with that? Okay. And the definition of logarithm says log base a of x equals y if and only if a to the y is equal to x. Okay. So that's nice. All right. Now what we want to do is a little bit of manipulation here. And you're not going to maybe understand right away why we do this, but look at our blue statement up there. Our argument becomes a, right? Currently what we have is m to the x equals a to the c. We need to get that a to the c to become a. How can I take a to the c and let it become a? How do I do that? Think about this. What if that c was a 2? What would you do? It was a squared. What would you do to make it a? Take square root, right? It was a to the third. What would you do to make it come a? Cube root. If it's a to the fourth, you would take the fourth root. Okay, so taking the square root is the same thing as raising to what power? 1/2. Taking the cube root is the same as raising to what power? 1/3, right? So basically what we want to do to make that a to the c become just a, we want to take the cth root. Does that make sense? Okay. Now, if I want to do that, I am going to actually, instead of taking the root and using the root notation, I want to use the exponent notation. So what should I raise that to so I can get it to become a? What did we just say? If I take the cth root, if I was going to take the square root, I'd raise it to a 1/2, right? So if I take the cube root, I'd raise it to a 1/3. So I take the cth root, so I raise it to the 1 over c. So I'm going to rewrite this as a to the c raised to the 1 over c. Now, if I'm going to do that to the right-hand side, I have to do it to the left-hand side, right? Okay, I have to keep the equation balanced, right? Okay. Those three little dots like that stand in for the word therefore. Okay. So m to the x equals ac, then m to the x over c equals a to the c over 1, or a to the c raised to the 1 over c. So therefore, m to the x over c is equal to what? It's just a, wouldn't it? Okay. I want to write it as a to the c over c and multiply these two things together, power to a power, but c over c is just the one I was looking for. Okay. Now, what's nice about that is that a is going to become that a right there. Once we then apply that definition in reverse order. Because right now, what we have is that, right? Let's apply it in reverse order. I'm going to rewrite it as log base m. Remember, this becomes my argument. Is equal to x over c. Remember, this exponent here is over on the right-hand side after I transform this into a logarithm. Okay. How can I solve for x here? multiply both sides by C. So I'm just going to bring my work up here. Multiply both sides by C. I get C log base M of A is equal to X, right? Did we start with the left-hand side, and now we've generated the right-hand side, right? So what did we let X be at the onset? It was this thing here, right? Can I make that substitution again? C log base M of A is equal to X, which X we said was log base M of A to the C. Is that the law that we set out to prove that I wrote in blue? Does that make sense to everybody? Okay. So that's an algebraic proof to show you that regardless of what you use as M, A, and C, that law should be true all the time. Okay. As long as, now understand this, I can't have on the right hand side, can I take the logarithm of a negative number? No. Okay. So let me show you what this is stating for us. If I just choose a slider, let's go, whatever, doesn't matter. I want M as our base. Put M, A, and C as our exponent, right? So now it's saying if I take log base M of A to the C. Right now it's going to be undefined. We'll talk about this because all those are ones right now. And then I take C times log base M of A, should be undefined again, okay? If I start changing these values of A, M, and C, okay, so right now what I've got in behind that is, that was the first one I typed in, that was log base M, so M is 7.7. Of A, so 7.9 to the 6. And then this one here, I have 6 log base 7.7 of 7.9. Does that make sense? Okay. And as I change that 6, that 7.7, 7.9, for both those, they're going to adjust the same way. Do I always get the 6.08 and 6.08, those values in those positions of A and B, to always be the same, regardless of what A, B, and C are? That makes sense to everybody? Now understand, like A cannot be negative. I can't take the logarithm of a negative number. So that's why when I get A to be a negative 4.7, it goes undefined. Okay? But that's the logic behind that law, is that regardless of what your base, what your A value or your argument is, and what your exponent is, you can apply that property. You always get a true statement. Okay? You get equivalent values. So I think it's important to understand that, right now I'm going to make the argument that with algebraic proofs that maybe we've done so far this year, we're hopefully getting better at them. If we're not getting better at them, my hope is at least we're understanding and getting the appreciation for the fact of where a lot of our algebra comes from, okay? And not so much to say, oh, someone just made it up and it works, okay? There's logic, there's reasoning behind why every one of our properties, laws, theorems, definitions, why they work and in the way that they work, okay? And they're all explained through proofs like that. I think, I don't know if I told you this yesterday, I think in regards to algebra, proofs like that are more, and understanding them are more important in our algebra than being able to do these practice problems, okay? Because an understanding of why is a better thing to have than just doing, okay, and applying. So, I think did we do this first one yesterday? Okay, well, basically all I want to do for the rest of the period is go through a series of examples numerically and algebraically and show how we can maybe work through them and see how we can maybe check our results, okay? This expansion and condensing of logarithms and logarithmic expressions is going to be essential for the equations that we deal with on Monday, okay? So this first one, it is a addition, okay? So we have to condense this, okay? It's expanded right now. We have to condense. So I'm going to rewrite this as log base 4. It's addition, so that turns into what? Multiplication. So I have 2 times 32. Okay? Well, that is equivalent then to log base 4 of 64, right? So at this stage, we ask ourselves this question. If I start with that, I'm now going to apply my definition of a logarithm. Let's say 4 to what exponent should equal 64? And you told me yesterday that should be what? Should be 3. Okay? You ought to be able to take the calculator now. I'm just kind of showing you the different calculators that you might have access to. And you have, this is the thing, you have to know how the device that you're using operates, okay? Just kind of drawing comparisons here to GeoGebra to other technology, okay? GeoGebra, if I type in log, it gives me that understanding of my syntax. It's how I have to type it in, okay? The command says that you have to type in your base first, okay, and then your argument. So argument was 64, right? We get 3. Is that the same thing as log base 4 of 2 plus log base 4 of 32? They should both give me back 3, right? And they do, okay? Now, if I'm on my TI 8384, depending on which model you have, you might be able to do this, you might not be able to do this, okay? If I have the 84 Silver Edition, okay, like the most, and you can, I don't know if anybody's done this, you can update your operating systems on your calculators, okay? You have to have the cable to link to your computer, the USB cable, and you got to go to TI-83's or TI's website and find the operating system, download it, and all that kind of stuff. There are tutorials on how to do that. But if I've got the most basic operating system, I go to mode, basically the way I'm going to figure out whether I've got this one or not. If I go to mode, and you see how if I scroll down, it's only one page of things I can scroll to, that means I got a very basic operating system, okay? So when I go to logarithm and hit the log button, it's common log. If I go to math, I'm going to scroll down. Under math is where your log functions exist, and there are no additional log functions under math, right? So with this one, I cannot do base 4, okay? Unless I do a little preliminary change of base formula work first, okay? And we'll show you how to do that next couple days. If I have a TI-84, but I got a little bit newer operating system, okay? If I hit mode, see down there where it says next at the bottom, that means I have multiple pages. That means I can go to an option that says math print or classic. Now, if that's the case, then I can hit the math button. I can scroll all the way down to the bottom and see where it says log base. I can hit that. And if I'm in math print, it will actually insert we call that latex, okay? Latex notation, or just the way you see it, okay? They use the word math print, and that's basically a good way to compare or create an analogy to what latex is. But if I go base 4 of now, like we said, 64, gives me 3, right? Okay. Now, if I'm not in math print, or I'm not using that latex idea, so it would look When I go to math and I go down to log base, it's going to do this, okay? Now here's where you have to understand how your different technology is programmed. GeoGebra says type in your base first, comma, your argument. This says type in your argument first, then your base. And then I get my 3, right? Okay. Hopefully you would realize that if you knew how, like maybe GeoGebra was working, and you thought, well, I got to type in 4, comma 64, and then you hit enter. You obviously see that you don't get 3 back, right? That you knew that you should get back. Okay, so that should maybe be the identifier to say I got the order of my base and my argument backwards. This would be the base of 64 and an argument of 4. Okay, you have those tools. Desmos. Worked a little bit with Desmos in last period. Let's see here, clean this up. Nope. I'm not all that great at Desmos. But if I just type in log, okay, see it doesn't show me like GeoGebra does how I type things in for a base. I don't know if I click on that. It says function log requires an argument. Okay, so it looks like it's only allowing me to do log base 10. Okay. If you go to functions down here, go to your miscellaneous, you do have a log base A option. Okay. But you see there that I don't have like a command that I can just type in, right? I have to go to that function. So I can go now 4 of 64, and I get my 3 back that way. Okay, so just understanding the kind of dynamics of the different technology that you might be using to help yourself out. Because some of them are avoidable or unavoidable. This one, I think that should be a fact that we know, 4 to the third of 64. Okay, in the next one, it's a fact that we should know. But in that last one, C, I don't think we're going to know that fact. Okay, B says it's subtraction, right? So log base 2 of, how am I going to rewrite that? If I have subtraction, it turns into what? Division. So I'm going to rewrite that as 80 over 5. So 80 over 5 turns into what? 16. So I got log base 2 of 16, right? So 2 to the what power will give me 16? 4. Okay? 2 times 2 is 4, times 2 again is 8, times 2 again is 16, right? All right, so that one, again, 2 to the what equals 16. I think that should be a common knowledge type question. Now when I do this last one, what's the base of this one? 10. So I'm going to rewrite this as log base 10. Now it's going to be 8 to the negative 1/3, right? If we've got that multiplier out front, when I condense, it becomes an exponent, right? And it's an exponent of my argument. Okay. Okay, now what do I do with a negative exponent? Don't I drop it down to the denominator in this case? Okay. What is 1/3 as an exponent? What does that really mean to me? 8 to the 1/3 is the same thing as what? The cube root of 8, right? What's the cube root of 8? 2. Okay. So now I've condensed my argument down to one value, right? That's the purpose of doing this. The question is, what do I raise 10 to get back to 1/2? Well, that means I've got to take 10. If I raise it to an integer, okay, a positive integer, it's going to grow to, or it'll be a 10 or 100 or 1,000. How do I shrink it? Okay, well then my exponent has to be a fraction, correct? Okay. Does anybody have off the top of their head any knowledge about what I have to raise 10 to turn it into 0.5? Probably not. Okay. Like we have 2 to the 4th, we know that gave 16, right? That's common knowledge. What power I raised 10 to get 1/2 is not common knowledge. So this is where we got to grab our calculator. And the purpose of this question, why they let it be a common log, is that they're assuming that the most elementary calculator you have will at least use common logs. So if I say log base 10 of 1/2, that's that number right there. Okay? Negative 0.3. I kind of hate Desmos because I can't zoom in on the results here very well. But here's the idea. If I take 10 then raised to that number, hit enter, does it give me back 0.5 then? Okay, so that's validation that we're doing the right thing here with our calculator. Questions on that? All good? Okay. So that's when they say evaluate. Okay, you've got the knowledge to change those things down to one single value. Okay. Now, when they say expand or simplify, okay, we're not necessarily looking for now one concrete value. Okay. We'll go through these 3 examples, but once we finish each one of them, I want to go back and use either GeoGebra, Desmos, or TIA 384 and see if we can use that device to validate our properties. And this is going to be kind of provide you insight to what you would do if you're on a test or a quiz in this class or any other class, and you're not certain about your algebra. Okay, if you're not 100% certain what to do, I would try something, right? Okay, I wouldn't just leave it blank and go to the next question. I would try something that I think would make sense. And if I'm not confident whether that thing is actually a valid algebraic process, I could then start to maybe use some specific values and see with what I started with and what I end with those specific values are the same result, the same quantity, then I know what I've done was correct, right? If they're different, then I know what I did was wrong and I try something else until maybe I have enough time to whittle it down to the right procedure, okay? So this is what I'm saying. Let's just do part A here. I go log base 2 of 6x. They say expand, so 6 times x. That's A times B, right? That's a product. So products turned into what with logarithms? Addition. They turn into sums, right? So we'll take log base 2 of 6 plus then log base 2 of x. And that's the expansion. All right? The question is, did I do that right? And we did, but let's say this. Is that true? Well, what does x represent? A variable, right? On this side here, let's choose x to be a variable. What am I not allowed to choose it as? Can't use 0 because that's an asymptote, right? And I can't use negative numbers, right? And I don't necessarily want to try 1. Okay, 1's going to be, you might want to stay away from that. Try 2, try 3, try 4, try a number that is to the right of 0, right? Does that make sense? So let's just let x be 2. All right. So now if I take one of my calculators and I type in log base 2 of 6 plus log base 2 of 2, that's my x, right? Hit enter, see what I get. Can I then say the right-hand side, log base 2 of 6 times my 2, my x that I chose. So I'm keeping that variable constant on this side and that side, right? So kind of my controlled, if we're doing a science experiment, you call it a controlled variable, right? Leaving my variables the same numbers on the left-hand side and the right-hand side is that controlled variable idea. Hit enter, I get 3.58 both times, right? So this time, this one here evaluated the left-hand side with x being 2. This one is the right-hand side with x being 2. They equated, so that means that these two are equal expressions, right? If they were different, does that tell me that they were unequal expressions and I've done something wrong? Yeah, okay. So let's do the same thing then with this one, okay? Now, you see in part B, x to the third times y to the sixth, right? You have multiple logarithmic laws existing there. Okay? Does anybody know which one is kind of the dominating one, the one we deal with first here? When we want to expand things, multiplication and division are the two that you want to address first. Okay? So we have multiplication there, right? X to the third times y to the sixth. So what I'm going to do is my x to the third is my A, and my y to the sixth is my B. Does that make sense? Okay? So I pull the multiplication apart as addition, or pull the division apart as subtraction in the future. Now, do I still have log properties or log laws existing here? Yeah, that 3 can come out as what? Or where do I put it? Yeah, I put it up front, right? So it becomes 3 log base 5 of just x, plus then 6 log base 5 of just y. Now our question is that thing there the same as that? So up here in this red one, or this top one, I guess, let's choose a value for x. Give me a value for x. 2. Choose a value for y. 3. It shouldn't matter, but what I like to do is if I chose x to be 2, I'm going to let y be something different. Does that make sense? Okay. It doesn't really matter, but just to keep things straight, I think that's a little bit easier of a procedure. So then in that top one, we'd be looking at the value. We go log base 5. Now I'm just going to type it in the way I see it. So x we said was 2, right? We go 2 raised to the third times then we let y be 3. So 3 raised to the 6. I'm not going to do any mental math, right? I'm going to let the calculator do all the work. Hit enter, 5.39. Okay? Now I'm going to come down to this bottom one. Okay? We go 3 times log. It was base 5 again. Okay? Now, my x was 2, right? So I'm going to let x be 2. Plus then 6 log base 5. We let y be 3. Correct? Hit enter. Get the same results, correct? So it tells me I've expanded that correctly. And that process of expanding and condensing works both ways. Okay? So eventually we're going to start with this part here and work back to this. You can do that substitution to see if you've done it correct either way. I think something that's valid to talk about, if I can get that back, I split it down too far. Let's see this one. If I go, let's just do that first one real quick. Log base, what was it? Base 2 of 6 x. So we said, what did we say? X was 2. So we got that. And if I go log base 2 of 6 plus log base 2 of 2, we got the same numbers, right? Okay, so again, this is going back to that first one there that we expanded. Let me do this real quick. Let me see if this makes any sense to you. If I delete out that 2, that was my base, right? Does it really matter when I'm checking to see whether I've expanded these things correctly or not? Does that base really matter? No. Okay. So if you're using your calculator, and this is the benefit of maybe having one of those or understanding how my calculator operates and how this information operates, if I have a very general basic calculator that only does log 10, log base 10, I can still check these things because the base does not matter in regards to seeing if I've expanded or condensed them correctly. Is that all right? Okay. Now, obviously, it does change the values, right? But I don't care about the values. I care about the fact that the values are equivalent to one another on the left-hand side and the right-hand side of those expressions, that equation. Let's do this last one. Now, natural log, you can leave it as natural log because we're just expanding it, so we're not going to be converting to the exponential or anything like that. So leaving it as natural log, I don't think is a thing that is going to be confusing. If you prefer to write it as log base e of then AB over cube root of c, and then work with that one, that's fine, doesn't matter. But what is the dominating operation occurring in this one? It's this division. Even though we have multiplication first, okay, that multiplication, okay, is just the numerator, right? We have a numerator divided by a denominator, so that division is dominant. We have to address that first. So what we've got here, if I expand this, it's ln of AB. Now the division turns into subtraction, right? ln of now the cube root of c. Is that all right, everyone? Okay. Now, when I take this one, that's multiplication, correct? So how's that going to turn? What's that going to turn into? Addition. So I have ln of A plus ln of B minus then, okay, so the cube root of C, is that the same thing as that? So whenever you see your root notation, guys, with logarithms, we're going to want to change them into rational exponents. Because that's now an exponent that can come out front, right? And now I've fully expanded that thing. Now here's my question. Understanding our algebra a little bit. If those are equivalent, they're only equivalent when A, B, and C on both sides are defined values. Does that make sense? Okay. So on the right-hand side, let's think about this. If I were to choose an A value, that is like -2. Don't care what B is, leave it as B. Let's choose a C value that is -8. What's the cube root of -8? Be -2, isn't it? Okay. What kind of number would you have in here for the ln on the right-hand side? What's a negative, or let's say B is positive. What's a negative divided by negative? Positive, right? So on the right-hand side, I have the ln of a positive number. That is perfectly fine to do, right? Okay. But on the left-hand side, we said A was negative, right? -2. Said B was positive. And now we've got -3 ln of, we said C ended up being -2, or I guess it was -8, right? The right-hand side evaluates. You can take the natural log of a positive number, right? Does the left-hand side evaluate? It doesn't, does it? I can't take the natural log of -2. I can't take the natural log of -8, okay? So only for values in which both the expanded version and the condensed version are defined for will these two things be the same. Okay, because on the left-hand side we'll have an undefined value, on the right-hand side we have a defined value. The reason I talk about that is because if I'm going to check to see if I've expanded this thing correctly, I have to understand that my A, my B, and my C values all need to be positive. Does that make sense? Okay. Even though on that right-hand side, if I take a positive times a negative divided by a negative, I still get a positive. Or if I take a negative times a negative divided by a positive, I still get a positive, right? Okay. It's because how we expand this left-hand side and these laws that we talk about, each one of these also has to be defined. Okay, so just be careful of that on your calculator. All right, so let's work the other way. Something like this. Okay. We're going from the expanded version now to the condensed version. All right. So in the last, when we were expanding them, addition and subtraction were things that we had to address first, right? Which if we're expanding, we're looking at the a times b and the a divided by b. Okay. Those were the things we had to address first, and then exponents came last, right? Well, when we reverse the order, now we're going to condense. We reverse the order of what's important to us. Now we're going to take care of the exponents first. Okay? So when I see 3 log of x, how am I going to rewrite that? I'm going to write it, so I'm going to come up here. It's going to be log of x to the third, right? Does that make sense to everybody? Okay? When I am condensing, I'm going to go through this. This is kind of what I do visually. I just kind of circle all my coefficients out front, and I know that then they're going to go all back to exponents. Okay? Now, just be careful here. They're going to exponents of the argument. They do not become an exponent of the entire logarithm. Does that make sense? Okay? So then the second one becomes log x plus 1 to 1/2, and that's good enough to write it that way, but a lot of people, I think, when we see that 1/2 right there, they think the whole log is getting the 1/2. That's only the argument. So I like this, like putting that extra set of parentheses or brackets in there so that you know exactly what is getting that 1/2. It's just the argument. Okay? So now I've taken my coefficients, wrote those as exponents. Now I only have addition left over, right? What does addition turn into? Multiplication. And it's going to be a multiplication of my arguments, right? So I'm going to take log, I'm going to take my argument of x cubed, and multiply it times my argument of x plus 1 to the 1/2. Okay? And that's an equivalent answer. That's a fine answer. But when I have rational exponents, when we want to condense our logarithms, a lot of times the overall question is to leave them in radical notation. So a lot of times we want to write this as log x cubed times x plus 1 underneath the square root, and that be my final result. Does that make sense? Okay. Try not to leave rational exponents. That's going to be a very, very critical thing for us to be able to do when we start solving logarithmic equations, okay? Because our logarithmic equation is going to start like option A or part A here in this slide, and then we have to be able to condense it down to what we just did so that we can use the definition of logarithms to get an equation. Does that make sense to everybody? Okay. That's going to be, kind of what we start with on Monday, is doing some very kind of elementary logarithmic equations, see how we can then build those to more and more difficult equations. But that process of condensing this is always going to be present. Okay? Let's do this one. This one's a little harder. How many parts how many logs are we dealing with here? 3 separate ones, right? We got 3 ln s, we got 1/2 ln t, and we got -4 ln t squared plus 1. So just like the last one, whenever I have those coefficients, I'm going to take them and turn them into exponents. I don't know where that 1/2 there. See if I can get. There we go. All right, so then it's going to be plus ln of t to the 1/2. But what's t to the 1/2 the same thing as? Radical t. Minus then ln of t squared plus 1 to the 4th. So there's nothing wrong with actually expanding that t squared plus 1 over 4. There's absolutely no need in doing it. Okay? So just leave it t squared plus 1 over 4. Okay, so now we've got addition and subtraction, right? Anybody remember how we address these? Say again? Which one do I do first? Do I do the addition first or do the subtraction first? Addition. Okay, if I were to do 2 plus 3 minus 5, order of operations says to do the addition and subtraction left to right as you see them, right? Okay, so that's what we're doing. We're doing order of operations. We're condensing numerical values, right? We're simplifying numerical values. ln of s to the third, I don't know what it is, but it's a number. ln of radical t, I don't know what it is, but it's a number, right? So when I add those two numbers and then subtract that third number, when I do that, when I have a one number plus a second number minus a third number, I'm going to do the addition first because that's how I see them left to right. So I always like to put brackets around these things and say, okay, now I'm going to add those together. And when I add those together, they're going to turn into, you guys agree that s cubed times radical t when I add them together? Because addition turns into multiplication, right? So this is my a term, this is my b term. Addition turns into a times b. Okay? Now, I have minus ln of t squared plus 1 to the fourth. So what can I do now between those two things? Turns into division. So this thing is going to eventually become ln of s cubed radical t all over t squared plus 1 to the fourth. Okay. Is that all right? We could, we'll run out of time, so I'm not going to do this. So I could go back through and say, okay, let S be 2, let T be 5, let T be 5. So those are the only two variables we're using. And then go through part B where it says 3 ln of input my S value plus 1/2 ln input my T value minus 4 ln input my T value plus 1. Evaluate, get a numerical response. Then go to that red expression, plug in the exact same S and T values, evaluate, get a numerical response, and I'm done if they're the same, right? Okay. One thing I would be cautious of if I'm going to, because that red one's going to be a mess to type in, right? Use a program that uses MathPrint, okay, or LaTeX. I don't want to type that into my TI-83 or A4 in classic mode because there's a series of parentheses that I'm going to need that need to be extra to make sure this happens. If I'm going to type it in on my TI-83, I need a parenthesis there. It's going to open that parenthesis. I'll need to close it. I need to close that first blue one. I'll need that parenthesis. I'll need that parenthesis. Down here at the bottom, obviously I need that one and that one. And I think it's probably going to be beneficial to put those two. Is that a lot of parentheses to kind of keep track of? If I use Desmos or use GeoGebra, it will show me whether I've typed those in correctly with those parentheses. All right? Have a great weekend. Thank you.